Our group project is inkjet printed nanocarbon for thermal management, and it was a capstone project to produce a highly efficient thin filmed heating system.
The product we created is similar to the defroster lines in the back of car windows. Our applications could reach further, as this can become a clear heater that can be applied to various applications such as glass and low voltage electronics.
Hypothetically, we could use them on airplane wings for de-icing. Originally, airplane wings are de-iced using many chemicals, and that's very expensive, whereas if we were to use this thin film heater incorporated into the materials of the wings, we wouldn't have the need to purchase many chemicals, and it would be a low cost, and airplane wings would de-ice faster than using chemicals to de-ice them.
So this here is our final product. We printed the carbon nanotube circuit onto the polyamide film using a everyday home inkjet printer. The materials used in this project was a carbon-based ink made of carbon nanotubes, and we decided on using carbon nanotubes for their superior electrical and thermal conductivities. Carbon nanotubes, specifically single-wall carbon nanotubes, are a graphene layer that are rolled up into cylinder shapes, and we use these to produce a highly electrical current that will produce heat.
We inkjet printed carbon nanotubes to evenly disperse the carbon nanotubes onto a substrate so that we could use the random alignment of the tubes to generate heat. The product we created is highly efficient because of the rapid heat up and cool down times and the high thermal coefficient of the material used.
We programmed an Arduino to take the data for this project. We utilized a thermistor to read the temperature and time from the heating system. So we took the data from the Arduino and we imported it into MATLAB. And from MATLAB we did several different tests relating the number of prints to the resistance, temperature, and power. This basically was our analysis for the product, for the different voltages that we applied to the circuit to see if it worked at higher voltages and what the highest temperature we could reach at a given voltage.
To test how our product worked, we printed 4 different heaters. The first heater would be 100 layers of print. We run the polyamide through the printer 100 times. Then we do another heater with 200 prints, and then 300 prints and 400 prints. The results we got was that the 300 layer prints were far more effective than all of the other prints when applied to 25 volts of power. After applying 25 volts to the 300 print heater, it rapidly heated up to 163 degrees Celsius, then rapidly cooled down to room temperature.
Our project followed our 2 classes of engineering seminar and engineering capstone. Over the 2-year process, we formulated an idea, created a method to perform the idea, and produced a product at the end of the project. For this project, I was the group leader, and I helped facilitate the 6-member group, worked with time management for our large group, and helped with production of the product.
In this project, I helped set up the Arduino board with the programming and the production of the heater. So what the Arduino board does, it records the temperature over time of the heating process and the cooling process of the heater using a thermistor.
We did run into some limitations for our project. One was our printer that we selected. We chose a very low model printer. If we could potentially continue this project if we purchased a benchtop printer, and that way we could print on full sheets of polyamide and test further for that.
Our project was presented at the Materials Science and Technology Symposium, and we are hoping that our project is published in their peer-reviewed journal.